Hello everyone. So I welcome you again in this lecture, and today we are going to talk about shortest path in the graph. Finding the shortest path in the graph is very important to solve many problems. By finding the shortest path in the graph, we are able to solve traveling salesman problem. It can also be used for scheduling the task. It can also be used for finding the optimal distance between the two locations. So we'll see in this lecture what are the things that are important concerning to shortest path. So let's start. So the very first thing to understand is the path, that what is path in the graph. So path is basically a sequence of vertices that can allow us to reach from one vertex to another. Or formally, the path is defined as a sequence of vertices with the property that each vertex in the sequence is adjacent to the vertex next to it. So path is basically provides a route to move from one vertex to another vertex in such a way so that we have to go through a sequence of vertices so that each adjacent vertex is actually the neighbor of the other vertex. What does it mean? It means if I want to go from v1 to vn, and to reach to vn we need to go through sequence of intermediate vertices that can uh, allow us to reach to n. And here you can see these intermediate vertices again are arranged in such a way so here you can see that v1 is the neighbor of v2, v2 is the neighbor of v3, v3 is the neighbor of v4, v4 is the neighbor of and the next adjacent node. So by connecting all these adjacent nodes we are able to reach to the destination, and these sequencing of these vertices that allows us to reach to the destination makes a path. So the path we are representing uh, mathematically as that P is basically represented as a set of vertices which actually allows us to reach to the destination. So let's say we want to go from V0 to Vn, then the entire path will be defined as a set of all intermediate vertices that actually comes across from V0 to Vn. So here the path P of length n from node u to b is written as v0 to vn, where v0 we are assuming as u and vn we are assuming as v as small v, and our intention is to go from u to v. So it is defined in terms of n plus 1 node, and you can see that v is actually the vn and u is v0. Vi minus 1 is adjacent to v of I for, and it is applicable for all intermediate vertices that we see in the graph. Then there is a term called simple path. Simple path means that if all the nodes in the path are distinct, so if you are moving from one vertex to any other vertex, and if you are only using intermediate vertex only once, so all the vertex that come across from the source to destination are unique or distinct, then this kind of path is said to be a simple path. Means there is no cycle or no repetition of vertices are allowed in the simple path. Cycle, a path in which the first and the large vertices are same. So if you make a path, if you construct a path to move from one vertex to any other vertex or to the destination vertex such that the source vertex and the destination vertex is same, then it is said to be a cycle. For example, if I want to move from v1 to v2 to v3 and then from v3 to v1, then this edge actually constitute a cycle. So here if the cycle is simple, then these intermediate vertex are allowed to only appear once, means all the intermediate vertex are distinct. But if it is not a simple cycle, then these intermediate vertex are allowed to be occur or used more than once. So we have seen what is path, what is simple path, what is cycle. Now we will use these terms to understand the shortest path in the graph in a better way. We already discussed in our previous lecture that what is graph. Graph is basically defined as a set of two elements V and E, where E is a set of vertices and E is a set of edges in the graph. And then we have two kind of graphs. We have undirected graph, we have a directed graph, and let's say we are talking about directed graph, which is also called as digraph. In the Directed graph, the edges are having one arrow sign or one direction that defines the connection from, or that defines the path from one vertex to another vertex. What does it mean? So if I talk about directed graph, then let's say we have two vertices or the three vertices in the graph, then the edges will be having one arrow. That means we have a path, or we have a connection available from A to B, and it does not mean that you can also go from B to A. So if I make something like this, that means you can go from A to B, B to C, and C to A. But if I make something like this, that means this is undirected graph, and this edge means you are allowed to move in either way. You can go from A to B as well as B to A. So when I say DI graph or digraph or directed graph, then edges will have direction that defines the connection between the vertices. The shortest path between the two vertices is a path with the shortest length. So when we look at the graph, and if we want to move from one vertex to any other vertex, there may be many different possibilities are available there. For example, if I want, let's say, I will make one graph. Now if you look at this graph, this is a directed graph, and if I want to go to this vertex D, now to move to vertex D, we have many possibilities. In this case, if we look at this, we have one possibility is uh, A, B, C, E, and D. This is one. A, B, C, A, B, C, E, and D. And the other possibility is A, C, E, D. And the next one is A, B, D, E. So in a graph, there may be many different paths are possible. Path means from the source to the destination, we must have a connection, or we must have the edges that can allow you to reach to the destination. So there are many paths are possible, and the shortest path refers to the path which has the minimum value. Now in case of the weighted graph, in the weighted graph, the shortest path will be defined by the least cost, or the least weight of all the edges. Means you can add all the weight of these edges, and whichever is least will be the shortest path. But when we talk about the unweighted graph, where we don't have assigned any weights to these edges, in that case the minimum number of edges will define the shortest path or the shortest length. We are also calling as a link distance. Now what does that mean? So let's say if I take this scenario, let's say I'll, for simplicity, I am going to make only a undirected graph. Let's say this is one scenario. Now this is your source and this is your destination, and if I want to reach to D, and so we have two possible ways. One is I can go from here, then here, then here. This is one path is available, or the other path is I can go from here. So I have, this is one path, I am calling this as a one path, path number one, and second path is this, I am calling as a path number two. Now this if this graph is unweighted, means I am not going to assign any weight to the edges, then this path is said to be the shortest path or the optimal path, because here to reach to this D we have to go 1 2 3, but here we have to go only through the two edges. So when the graph is unweighted, we will see that a minimum number of edges in the path will give you the optimal path. But if I give some weight to these edges, then we have to check that what is the minimum value. For example, it is 10, this is 20, and this is 1, this is 2, this is 3. So if I follow this path, then the cost would be 30. I can simply add the weight of these edges, so this makes 30. But if I go through path 1, then 1 plus 2 plus 3, that is 6. So in that case, this will be the optimal path or the shortest path. So it all depends that the graph is weighted or not weighted. So let's look at how we define the weighted graph. So already we have discussed in detail in the previous lectures that graph is defined as this, and weighted graph means that we are assigning some weights or value to the edges, and these values represent the cost. Now this cost can be anything. It can refer to uh, the effort to move from one place to other place. It may also refers to the time to move from one place to another. For example, if I say A to B and this is 3, so this is defining the cost. Now this cost can mean anything. It can represent the time to move from A to B. It requires 3 hours or 3 minutes. It may requires cost. It may requires money, that in order to move from A to B, you will require like $3 or some three unit of currency. So this three will be the effort or the cost required to move from A to B. So we are having one function W that defines the value of this weight. So in this function we need to pass the edge, and it will return the value of this edge, and this value is basically referring to the weight. So if AB is the edge, then if I write WAB, then it will return the weight of this edge. This is 3. So the length of the path is the sum of the weight of its constituent edges. So if I want to find out the cost of the path, or if you want to know the length of the path, it all defined by adding the weight of all these edges that constitutes within the path. What does it mean? If I want to go from V0 to Vk, and this is V0, then V1, V2, then V3 up to Vk, and let's say we have here cost is C1, C2, C3, C4. So if I want to know what is the cost from V0 to Vk, then the cost is C1 plus C2 plus C3 plus C4 and so on. Means we have to add all the cost, or we can write as length of P, or you can say the cost of this path P is summation of I equals to 1 to K, this function W, and we are passing the edges Vi minus 1 to Vi. So Vi minus 1 because I starts from 0, so we are passing V0 V1 plus W V1 V2 plus and so on, W Vk minus 1 to Vk. This is how we can find the path of or you can say this is how we can find the cost of any path or the path length of any path. Then we refers the minimum path length. This is an important term that we are using while finding the shortest path, and minimum path is represented by del sign. So when I say del uv, that means we are referring to the path, or you can say the minimum path, the minimum cost, the minimum length to move from u to v. So del uv refers to some value if the path exists. So if it is, let's say, k, that means this is a minimum cost to move from u to v, and if there is no path exist, then the value is infinite. So if there is a path exists, then we will get del uv, and otherwise it will be infinite. So if you look at this, if I want to find out the length from A to E, our objective is to find del AE. So there may be many possible paths are available, but when I say del AE, that means I am looking for the minimum path, and it's already find out by using some algorithm that the minimum path is ABCE. So ABCE, which is 2 plus 1 plus 3, which is 6 here. So there are many possible paths are available. This is a simple graph, but in the if the graph is representing a real life problem, the graph may be complex, and it is not always possible to manually find what is the uh, shortest path or the minimum path length. In that case, we need to have some algorithm that will find us the optimal path. So we will be discussing some algorithm that will find the shortest path for us. We have variety of problems that is related with the shortest path. We will have a look on these algorithm. The very first kind of problem is single source shortest path problem. So here we mean to, for example, let us take one graph A, B, C, D, E, something like this. Okay, this is one graph given to us, and when I say single source shortest path problem, here means find the shortest path S from each vertex V. So here our intention is to find the shortest path from from one source. So our one source is defined, and for the source we want to find out the shortest path to every vertex. Means I want to find out what is the shortest path from A to B, A to C, A to D, and A to E. Okay, so for example, when we do the traversing using the breadth first search, we are actually finding the shortest path. There we have to take one node as a root, and from that route we find the shortest path or the minimum path from the root to every other vertex. Then second category or the second variant of this shortest path problem is single destination shortest path problem. Now this is just a reverse of the previous one. In the previous one we have one source defined, and from the one source we are finding the shortest path to every other vertex. But in the single destination, this is just an opposite of the previous one. In the second case, we have one destination defined. So let's say our destination is D. So we want to know that what is the shortest path from every other source to this destination, means from A to D, C to D, B to D, and E to D. So this is just a different format of the previous problem, single pair shortest path problem. So in this case, what we are doing, we are interested to find a shortest path from U to V for a given vertices U and V. So single pair shortest path means in the given graph we are only interested for a particular pair, and we want to know what is the minimum distance or the shortest path between these two vertices. For example, I may take my pair is CE. So my interest is to find out what is the shortest path between this pair C and E. So out of all available path, I am only interested to know the shortest path between C and E. This pair may be anything. I can choose my pair as A and B. So here only we are concerning to know the shortest path between the two vertices, not with every other vertices, as we have seen in the previous two cases. Now, if you think a little bit on all these problems are actually very much related to each other, and also we are solving these problems by using a Dishitra method. Dishitra method is a very popular algorithm to solve the single source shortest path problem, and also the different variation of the same problem can also be solved using a Dishitra method. Then we have other kind of problem that is called all pair shortest path problem. In this, find the shortest path from U to V for every pair of vertices. Now, in the single pair of shortest path problem, in this we have a defined pair, and we are only interested to find the shortest path between this pair. But in the all pair shortest path problem, our interest is to know the minimum distance between every possible pair in the graph. Means I want to know what is the shortest path between AB, between AC, between BE, between CD, between CE. So all possible pair that you can see in the graph, we want to know the shortest path between the pair. And for this we have various algorithms are available. For example, we have a Floyd-Borstel algorithm is there to find the all pair shortest path. We have a Johnson algorithm is there. These are popular algorithms which are actually used to find the all pair shortest path problem. Then we have some variation also, means some algorithms allows the negative weight in the graph. Some doesn't allow. Some allows the negative cycle also. Some does not allow. For example, when we talk about the single source shortest path problem solving by Dishitra does not allow the graph to have negative weight. Now this graph can have positive weight, also the negative weight, because it all depends on the situation. So if I say -2 is defined here, then this kind of graph is not good to solve by Dishitra. But then we have different kind of strategy or algorithm that is called Bellman-Ford algorithm. So depending on the problem nature, we have different kind of algorithms available to provide us a shortest path. So let's see what's next available. The other important property is optimal substructure property, which is again very important uh, into finding the shortest path, and this is also very much used in dynamic programming as well. Now what the property says here, we are defining the shortest path, the minimum path del UB by this relationship. So it represents minimum WP, that is the path U to V. So among all the possible path for moving from U to V, we will take the minimum, and that represent the del UV. If the path exists from U to V, then del UV represent to the minimum among all the possible path. Otherwise, it is infinite. Already we have seen in the definition. Then we have a theorem: subpath of the shortest path are always shortest path, and this also appears very obvious, because if we take any shortest path and if you take a subpath of the shortest path, that must be also the shortest. So we have some theorems like this. If p um, 1 to k is any path, so and this path is defined by the set of vertices v1 v2 up to vk be the shortest path from v1 to vk. So we are assuming that this path is the shortest path, and then the further we are saying that there is a path pij that defines using the vertices vi to vj be the subpath of p1k. Means we have one path v1 and vk. Okay, these are the two vertices we want to move from here to here, and to move from here to here we have to go through many different vertices. We have to go through sequence of vertices. Let's say we are going to uh, v2 v3 v4 v5 v6 v7. These are the intermediate vertices that actually constitute this complete path, and we are also claiming that this path is the shortest path, and this is just a subgraph of a bigger graph, and this is the shortest path. And then vi to vj, let's say this is vi to vj is these three edges with the subpath of p1k from vi to vj. Then pij is the shortest path from vi to vj. So the theorem claims that if this is the shortest path given to us, and if this is any subpath to it, then this is mandatory that this must also be a shortest path. So that means if I want to go from v3 to v5, then we don't have any other path other than this that is said to be a shortest. This must be a shortest path because this is a subpath of the bigger shortest path. This is the theorem, and is also very important, although it's very obvious also. So let us understand this through one example. So we have an observation that any subpath of the shortest path must always be shortest path. Why? This is also very obvious. We have just discussed about the optimal substructure property. So if you have any subpath from the given shortest path, then that subpath must be the shortest path. Let us also understand this here. Now, here we have possible path from A to E is A to B to C and to E. This is one path possible. Other path is A to C to E. Another path is A to D to E. Now, if it is claimed, now if you also let us write the cost of this. So this is 2 plus 1 plus 3, that is 6. And if I say ACE, this is 8 plus 3, this is 11. And ADE, this is 5 plus 4, which is 9. So we can see that this is the minimum value and this will be the shortest path. So if you are claiming that ABCE is the shortest path, this is the shortest path. That means if you want to go to A to C, now A to C is a subpath of this path. Now A to C will always be shortest through B. You cannot find any other path to go to C except from this. So if you want to go to C, we have two possibilities. Either you can go from here to here, or you can go directly from here. And because uh, this has already been proven that this is the shortest path, then definitely this must be the shortest path. A, B, C will be the only shortest path. Okay, so this is what we are trying to prove. And also we'll take one more example to understand in a more better way. Let's say A1, A2, A3, A4 and A5. These are the vertices, and let's say this makes the shortest path. Okay, now if I am claiming that to move from AK, now this is, we are assuming that A1 to A5 is the shortest path. This has already been proven here. Now let us try to prove this by contradiction, that any subpath of this path will always be the shortest path. So let's say uh, A1, A2, A3, A4, A5, this is the shortest path, already we have proven. And now we are claiming that A2 to A4, the shortest path will be A2, AK, A4. So not this path, but this is the shortest path. This is what we are claiming. Now, if we claim that this is shortest path to move to A to A4, it also means that in order to go from A1 to A5, you would have chosen A1, A2, AK, A4 and A5, not A1, A2, A3, A4, A5. So these two things are a contradiction or contradictory in itself. That's why we can easily uh, realize that the any sub path from the given shortest path will always be shortest. Okay. Then we have important concept called relaxation. Relaxation is very frequently used in all the shortest path algorithm. Now relaxation is an effort to make your path better. What, so how does it work? If the length of the new path from S to V is shorter than dV, then update the dV to the length of this new path. Now here we are using one term d of V, which refers to the distance, you can say, of the vertex V from the source. So if I say dV equals to 5, that means the cost of moving from the source can be anything, let's say U, from U to V is 5. If I say d of A is 9, d of B is 7, and my source is S, that means to move to A the cost is 9. To move to B from S, the cost is 7. So dV represent the cost from the source to this particular node. Most of the algorithm, when we work for the shortest path, we work with the relaxation. So relaxation is an effort where we are improving this value. When I say improving, means we are trying to decrease. Most of the time we are working with the greedy algorithm. So for example, the very popular algorithm Dijkstra method, which is already we have discussed, like BFS and the Prim's method. So Dijkstra is also very much similar to this Prim's algorithm, and it is also working on the greedy method. So in the greedy algorithm, we already discussed that in the greedy approach we keep on moving to the next stage by considering the best local choice. We select the option which is of minimum value. In doing so, there's a possibility you may have chosen the path which may be costly, and at a later stage you may apply that there is other better path possible, and through relaxation we can change this decision, because we are not having any heuristics here that will give you the entire picture, or you can explore the entire scenario or the entire graph, that which is the best path. So we are keep on moving with the greedy approach. Now what does it mean? The meaning of this is, let's say we have this graph A, B, C and D. So let's say this is 2, this is 20, and this is 1, this is 5, 50, let's say. So when you work with the greedy approach, what will happen? You will be moving from A to B. Actually, our objective is to move to D. So in the shortest path algorithm, we will keep on exploring all the possible ways. So when you are here and you have the option to move to B and to move to C, and you will compare that which one is minimum. So you may decide this is minimum, so you will choose there and you will say I go to here B, and you will set the D of B is equals to 2. That means the cost of moving here is 2, and then you will decide because our objective is to go to D. So you will go from here. So you will find here 50, and the cost here is 2, means this cost is 2 and plus 50, that means to move here the cost is 52. And so far you are assuming that this is the best path is available to you. But later when you keep on exploring the different possible options, and when you come across, you will find that this is actually better than this, means you can also go to D through this path, and that is 21. So with the DV, we keep on improving the value. So initially we have set the DV value of D is 52, but later stage, at the later stage, you will be going to improve this. You are going to update this to 21. That means to reach to D from A, the best path is costing 21. So this is how this relaxation is working. So D of V is the shortest path weight estimate, and it is upper bound on del SB. So if you del SB already we have discussed, it's a minimum cost to move from S to B, and DV is an effort to reach to del SB. So this basically tells the upper bound. So whatever the maximum value, the maximum possible weight available in the graph, it may take that value, but finally when you stop by using any algorithm, at last you will find that the dv value is actually equals to del of sb. So in the other sense, you can say that the d of b is the upper bound that can be maximum, is del sb can be maximum value with equals to d of b. So we will have to maintain d of b for each vertex of the vertex set of the graph. So initially what we are doing, so this is something which we are doing in all the algorithms. We are doing initialization. We have to pass the graph and also the source from where we have to start. So initially what we are doing, we are keeping the d value of v equals to infinite, and we are assuming that to reach to the vertex v there is there is no possible path, but we are keeping the d value of s equals to 0, means this is the vertex from where you have to start, and then applying the algorithm step what is given in the algorithm, we have to apply on this source, and then we keep on changing the dv value. And also we will keep a track of the predecessor of every vertex. This is called pi of v, which is the previous vertex. It will define that what is the previous node to reach to the v. What does that mean? It means initially when we are working with the greedy approach, so at this time we are saying that pi of b is a, that means to reach to b I should follow a, and here I have said the pi of d is b, that means to reach to d I have to follow from b. But later when we keep on exploring, we will realize that the better path is not from B to D but from C to D. So we will also update the pi of D is equal to C. That means the predecessor or the previous node to D must be C. Means to reach to D you have to go from C. So initially we set this nil, that means there is no previous node to any vertex, and D of S is 0. So this is the assumption that we take while we are working with the shortest path algorithms. So let us look through some properties of relaxation. So D of B will have the values. If not infinite, means if the path exists, then it will be representing the cost of the path, means moving from the source to that vertex if the path exists. If the path does not exist, then it will take value infinite. Now D of B will always be remain the same throughout the process or will keep on decreasing, because our effort is to keep on improving the value, means we are looking for the better possible path. So either the D of B value will remain the same or it's keep on decreasing to reach to the del value. So let S belongs to this vertex. So S is any vertex for all edges UV that belongs to this edge set. We have S to V from means this is the shortest path from source to vertex will always be less than from S to U plus WUB. So again this is again a true because it says that this is some sub path of the given bigger path. So it says that the del of SB, any minimum value from S to B will always be the minimum value of its subpath plus the weight of U to B. Now, we have many different algorithms for finding the shortest path, and the basic difference between this algorithm is that how they are using this relaxation procedure, how many times they are relaxing each edge. So only this thing will actually bring a difference in their approach, and they and the steps will be different to reach the solution. So there are two fundamental things that you will observe in the different approaches, that how many times they are actually relaxing the each edge and the order in which they relax the edges. For example, if you talk about the Dijkstra algorithm, in the Dijkstra algorithm we are only relaxing every time each vertex only once. What when we talk about the uh, Bellman-Ford algorithm, we are actually relaxing these vertices many times. So it all depends that what the algorithm is actually using it, and that actually defines the different strategy, and that makes the algorithm different. So if it is asked how many times each edge is relaxed in the B phase, then it is only one. How many times we are relaxing in the Dijkstra, then the answer is one. How many times we are relaxing in the Bellman-Ford, the answer is more than one. So it all depends that how what is the strategy is being defined by the proposal. This is all about the fundamentals of shortest path in the graph, and in the next lecture we are going to discuss in detail about the Dijkstra method, which is used to find a single source shortest path. That means we are interested to find from the source the shortest path to every other vertex. So we'll see in that that how the relaxation is used in that algorithm, and also we will apply the algorithmic steps in some example to see that how the shortest path is found to every other vertex from a given source. So this is all for this lecture. Thank you very much. Take care.